All right, we're ready to get started. So before we start today's lecture, I just want to spend like 5 more minutes reviewing what we discussed in our last lecture. So the entire chapter 6, we're trying to finally start talking about chemical reactions. Or when we're saying chemical reactions, we're talking about equilibrium chemical reactions. Or what we're trying to do is predicting what is going to happen at reaction equilibrium, right? What's the composition of different chemical species at equilibrium? How do we define equilibrium constant? How does equilibrium constant change with respect to temperature? Right, so in our previous lecture, we first did a quick review on chemical potentials by saying, hey, we discussed chemical potentials before, but for ideal gas, like gas phase, one species, like pure species, went over the derivation to show that my chemical potential is effectively the same as the molar Gibbs free energy. And since it's molar Gibbs free energy for isothermal processes, we have this expression here that your chemical potential change will equal to RT ln P final over P initial. Right? If we take our P initial as our standard pressure, we have our standard we have our standard chemical potential, or the chemical potential for a isothermal processes with respect to pressure equals to the standard chemical potential plus RT ln P over P naught for a pure chemical species. All right, and then we took one more step from talking about a pure chemical species into now let's think about ideal gas mixtures, right? So for chemical reactions, we want to have a mixture of your reactant and products together. So to describe our chemical potential, remember we have two different criteria, right? The first one is very straightforward to understand. The first one, just say PV equals nRT, just now my number of mole reflecting the total number of mole of chemical species. And then the second criteria here is we set up a special case to link the chemical potential of a species inside a mixture versus a chemical potential of pure substances, right? So the whole point here is we know how to calculate the chemical potential of a pure substance. What we don't know is how does that relate to the chemical potential in a mixture. Right, so for example, in here, let's say if we have A, B, and C in my ideal gas mixture. Right, let me just remove everything here. And on the bottom, in the bottom chamber, we only have gas A. Now the top chamber and the bottom chamber are being separated by a rigid membrane that allows only my gas A to permeate through. Right, so thinking about chemical potential as a function, right? So for the mixture, we know that the chemical potential of my species A, or any of my species, of this one-phase system, that's my partial differential of dG over number of mole of your chemical species, while temperature, pressure, and number of mole of B and C are kept constant, right? Or the other way to put it is we have my mu A in my mixture to be a function of temperature, pressure, my mole fraction of A, mole fraction of B, mole fraction of C, etc. All right? But it's really hard to evaluate this relationship because we have so many variables. But because we can set up such an equilibrium between the top chamber, that's a ideal gas mixture, and the bottom chamber, that is a pure substances, right? So for the bottom chamber, we only have one gas in there, right? So we have mu A, and this little star denotes this is a pure gas. All right, so now what is the function of my bottom chamber? This is something we know, right? So for our bottom chamber, this is equals to the Gibbs molar free energy of my species A, because we only have one species in my bottom chamber. And we know what that expression is, right? So that expression is something we went over before. So that's the standard chemical potential plus RT ln P initial, or some kind of P, over P naught. I'm just going to put P over P naught. Right, so that's what we did before for the pure gas in the bottom chamber. Now, the top chamber and the bottom chamber are in material equilibrium with each other, and that tells us something, right? What is happening when two systems are in equilibrium with each other, in material equilibrium with each other? Right, so they have same chemical potential, right? So that means what we want, which is the chemical potential of A in the top chamber, in the ideal gas mixture, must equal to the chemical potential of A in the bottom chamber, right? And at material equilibrium, we have the partial pressure of A equal to the pressure of A in that bottom chamber must equals to Pi, which is the partial pressure of A in the top chamber, and that equals to the mole fraction of A of the total pressure on the top chamber. All right. So I want to quickly, because it seems like this part is lots of people get confused because I got some questions from people, so I want to spend a little bit more time to further illustrate like what we did. We start from what we know, which is the chemical potential of pure ideal gas, right? And then we build this link between pure ideal gas and the ideal gas mixture that are in material equilibrium with each other. And because they are in material equilibrium with each other, their chemical potential must be equal, right? So we have a way to describe the chemical potential of one of those species in the mixture, inside that ideal gas mixture. So at the end of our last lecture, we went over to say, hey, that's our fundamental thermodynamic equation of an ideal gas mixture. Right, so we have mu I, which is the chemical potential of my species I, equals to the standard chemical potential plus RT times ln partial pressure over standard pressure. Now, what are these? This is the partial pressure, or that equals to chi I times the mole fraction times the total pressure of an ideal gas mixture. And the bottom, that P naught equals to 1 bar. All right, so that's what we discussed in our last lecture, which is first we want to set up what is ideal gas mixture. What do we know about a pure ideal gas? And what do we know now using the material equilibrium? What do we now know about the ideal gas mixture? Now we have your reactant and product mixed together, right? So we're ready to talk about next step, which is chemical reactions. Once we mix our reactant and product together, we're ready to have chemical reactions going on. So in chapter 6.2, we're talking about ideal gas reaction equilibrium. So when I say ideal gas reactions, we're talking about both my reactant and product are all ideal gases. There's only ideal gases present in the reaction chamber. Now, the real life is obviously more complicated, but this is the starting point. We'll use the most simple scenario to do our definition of terms. Right, so a bit of review we did last time, like for a chemical reaction, where it's like Z0 goes to stoichiometric coefficient times your reactant or product, right? Stoichiometric coefficient that's positive for product, negative for reactant. And what else do we know about material equilibrium or reaction equilibrium? We start by saying, hey, we know that at material equilibrium, the sum of my chemical potential times the infinitesimal change of number of mole of species must equal to 0. Then for reaction equilibrium, we know that the dni equals to the stoichiometric coefficient times the extent of reaction, right? So that dc tells you infinitesimal change of the extent of the reaction. And we did our derivation to see like, okay, so this sum of my chemical potential times the stoichiometric coefficient must add up to be 0. So that's something we know. In addition, we also have our general the fundamental thermodynamic relations to describe the chemical potential of ideal gas mixture. right? So we have these two pieces of informations. And then in the next part, we will be using these two equations and the sample ideal gas reaction where we have AA plus BB goes to CC plus DD. So we'll go over the derivation together and see how do we define equilibrium constant. So I'm going to do that on the board. I'll keep these equations here because these are the information you need to do the derivation. And if you're watching the recording, you can see the derivation result on my annotated notes. So I'll do it together here. The first thing first, right, so what do we have in here? We have that the sum of my stoichiometric coefficient times the chemical potential equals to 0. Right, so for that chemical reaction, we have AA plus BB go to CC plus DD, right? So my stoichiometric coefficient for A and B is thus equals to negative A. That for B is negative B. Stoichiometric coefficient for C is C. That for D is small d. And I hope people in the back can see my handwriting. It's a little bit small. If you can't see it, you can come a little bit forward. Now from here, what else do we know? Let me just write out this sum, right? We're gonna have 4 terms. So if we write out that term, we have C, mu C plus D, mu D minus A, mu A minus B, mu B equals to 0. Just writing out that summation into things we know. Now in here, do we know, we already write out our stoichiometric coefficient. What about my chemical potential, right? We have our equation for chemical potential we can refer to, right? So now we're just writing out, right, what is mu C, mu D, mu A, and mu B using that chemical potential equation. All right, so what does that give us? Now in front of C, I have the standard chemical potential of species C plus RT ln partial pressure of C over P naught. Right, so this thing is giving me mu C. And doing the same for mu D, mu A, and mu B, we got the standard chemical potential of B plus RT ln PD over P naught minus A mu A naught plus RT ln PA over P naught minus B times mu B naught plus RT ln PB over P naught. Right, nothing fancy, just write out the equation like 4 different times, so we're just plugging numbers. And then on the right-hand side, this summation equals to 0. Right, so I want to organize my term a little bit. So I want to put all my logarithm functions to the right-hand side, and everything else, my standard chemical potentials, I want them to stay on the left. Right, so if I take all my standard chemical potentials out to put them on the left, so we have C, mu naught C plus B, mu naught D minus A, mu naught A minus B, mu naught B. So I'm just taking all these terms and stay where they are. Everything else, I move it to the right. On the right, we get negative RT times C ln PC over P naught plus D ln PD over P naught minus A ln PA over P naught minus B ln PB over P naught. All right. Now we have an equation. So whatever on the left equals to whatever on the right. And now the question we're trying to ask ourselves, what are these terms that we just write out. Right, so if we focus on the left one first, so what are these terms? If we focus on these, like this little symbol, right, mu naught C, what is mu naught C? The physical meaning of that is the standard chemical potential of a pure substance, C, D, A, or B, right? So these are the standard chemical potential of a pure substance. And what do we know about chemical potential of a pure substance? It's only one phase, it's all ideal gases, right? So what do we know about the nature of chemical potential of a one substance, one phase item? That equals to our molar Gibbs free energy, right? So for this one phase, this equals to my C, which is G naught, molar Gibbs free energy at certain temperature T of species C. So what does each term mean? So this one is my stoichiometric coefficient. Little m tells me that's a molar Gibbs free energy. The naught tells me that's a standard state, pressure equals to 1 bar. Temperature tells me it's specified for a certain temperature, right? So we come up with this equation talking about that isothermal processes. So temperature must be a set temperature, like a defined temperature. And the C tells me that's a molar Gibbs, standard molar Gibbs free energy of my chemical species C. So when writing it down, know what each subscription and superscription mean in the equation. We can do the same for the rest of the terms. Right, so these are just rewriting my chemical potential into molar Gibbs free energy. Now, that's a sum, and this looks very familiar. The sum is effectively the same sum if we write the stoichiometric coefficient times the molar Gibbs free energy of species I at certain temperature. Right, so these two are the same. Or, what is this sum? That's the delta G of the reaction. Or that's our standard molar Gibbs free energy of the reaction. Right, so that's the kind of thing you get by reading the appendix table when we discuss how to calculate the delta G of the reaction. That's what we're calculating. So that's the left part. What about the right part? Right part looks like it's just lots of like logarithms like adding up to each other, but we want to move, let's say we want to move everything inside to like one logarithm function. And a little bit of the review on logarithm mathematics is like if we have like x law in y, like outside the logarithm, you have x law in y. If I want to move that x inside, it's law in y to the power of x, right? So that's the logarithm function. Or if I have like law in x plus law in y, and that's effectively the same as law in xy. Or if I have law in x minus law in y, that's the same as law in x over y. That's a mathematics review. But if we are using that operation to try to move everything inside to one big logarithm function, on the right-hand side, we can simplify that to be negative RT ln, and then we have PC over P naught to the power of C, and then PD over P naught to the power of D divided by PA over P naught to the power of A, PB over P naught to the power of B. Where again, P naught here just our standard pressure equals to 1 bar. All right. And now we're ready to define our equilibrium constant. Now, whatever inside my logarithm, these are my equilibrium constant. Or that's our pressure equilibrium constant, Kp naught. right? So in this section, we used a sample reaction, which is AA plus BB goes to CC plus DD, and demonstrated like by just using the fundamental expression of ideal gas mixtures, we can come up with an expression of the, we can come up to define our equilibrium constant, have a relationship. What is equilibrium constant? Tells us a composition of different species at chemical equilibrium, right? And on the left-hand side, we have a thermodynamic state function, which is the delta G of our reaction. And we're ready to further simplify whatever we put on the board into our general reaction form, right? So we're just extending whatever we did on the board into, say, now for any kind of reaction, right? For anything that's zero, go to the sum of your stoichiometric coefficient times your reactant or product whatsoever. We still have my delta G naught of the reaction equals to negative RT ln K naught P. Note that this is the molar delta G of the reaction at certain temperature. And the definition of our Kp here, this gives us the product, so this big sign just tells us it's a product of your partial pressure of different chemical species at equilibrium over the standard P naught to the power of its stoichiometric coefficient, mu I. Right, so in here, like this term, let me just give you a simple example, right? So if I write something like this one, for like AI, it basically just tells me it's a product of like A1, A2, A3, all the way to AN. Nothing fancy, just a product of together, right? And in here, note that our stoichiometric coefficient is on the power. Again, that's negative for reactant, positive for product. You'll also see people write this top equation in a different format, which is if I want to express my Kp, the equilibrium constant, as a function of Gibbs free energy, that's a exponential to negative delta G naught over RT. All right. So here's our definition of equilibrium constant, and that's what we know about equilibrium constant and Gibbs free energy of the reaction. Let's do one example together to see how do we use these terms that we just defined to like work on a real example, right? How to use these information. So here I'm gonna spend some time just go over like how do I set up the problem and say like what is the things you should be thinking about when you're reading a problem together, and how to set up a problem, how to set it up correctly so you're on the right track. So let's read it together. We have initial number of mole of O2 gas. It's placed in an empty 32.8 liter container, so volume is set, and equilibrium is established at 4,000 K. And then we have one, find the pressure is 2.175 atm. So we know the pressure, volume, and temperature at equilibrium. All right. And the question asks us to find the equilibrium constant, standard equilibrium constant, and delta G naught for this dissociation reaction where my O2 gas dissociate into elemental oxygen at 4,000 K. Ask for Kp naught and delta G naught. So when looking at this kind of question, something you can instantaneously write down, right? For example, we say like assume ideal gases. So it's an ideal gas, and we have potentially two different species because we can have decomposition of O2. So for ideal gases, we have PV equals to N total RT, right? And my N total equals to number of mole of O2 plus number of mole of oxygen, okay, elemental oxygen. And looking at it, what we're looking for is Kp naught and delta G naught. And we also have a relationship that links these two together. Right, so we have our delta G naught equals to negative RT Kp naught. All right, and now we want to ask ourselves a question. Which one should I start first, right? Should I calculate Kp naught first or delta G naught first? So in this question, what are we able to calculate delta G naught, the Gibbs free energy of the reaction? One of the common mistakes is jump too fast into the appendix table and try to find the delta G naught and did it the reverse way. This one is not applicable because in our appendix table, right, we can look at it together. Do I have it? One second. Here we go. Right, so in our appendix table, this is the standard state thermodynamic table at 25 degrees Celsius, but our equilibrium is established at 4,000 degrees Celsius. So we cannot directly use the thermodynamic table to solve for delta G of the reaction. Right, so this is like maybe, but it doesn't work because the thermodynamic table is not at 4,000 K. Okay, so now let's go back and think about what else can we do. What else can we do? Now in here, what is the definition of Kp naught? Right, so this is the product of my partial pressure over my standard pressure, right? So that's the product of my Pi at equilibrium over P naught to my stoichiometric coefficient. So that means if we know how many number of mole or what is the partial pressure of my O2 and elemental oxygen at equilibrium, we will be able to solve for their partial pressure and consequently the equilibrium constant. All right, and do we have enough information to solve for the partial pressure of these two chemical species at equilibrium? Well, yes, we do, right? We know what total number of mole of species are. We know the initial number of mole of oxygen. We can use this information to calculate the extent of reaction. Right, so by simply looking at the problem and observing, like, what are the information I know? What kind of things I can do? I can write it out. Okay, so first thing, I want to solve what is my N total, right? So my N total, I want pressure, volume, R as a constant, temperature at equilibrium. And this is something we can do. Right, second step, once I have the N total, I can solve for the extent of reaction. So that's stoichiometric, right? You have initial state, the change, and then the final state. And we know what the total number is. We know what the initial number is. We will be able to solve for the extent of reaction. And we have enough information. Thirdly, once we solved the extent of reaction, we know how much oxygen has been transferred to elemental oxygen, right? So in this case, what we can find the Pi of O2 and Pi of elemental oxygen at equilibrium, right? So that's Pi equals to the mole fraction times the total pressure, right? Mole fraction we can calculate after we solve for the extent of reaction. Total pressure, that's a number that's provided in the question. So we have enough information. Right? And then it becomes very obvious, and then we can say like, okay, so we can solve for Kp naught using its definition and delta G naught using negative RT ln Kp naught. Right? So that should be the logic to go where you're reading a problem and try to say, okay, how do I approach this question? All right, and now we can do the problems together. Just want to go over with like, what is behind our mind when we're looking at a problem? What's the most efficient way to do it? You don't have to get it right the first time, right? It might be looking at it like, why I can't calculate delta G? And you realize, oh, because it's wrong, it's different temperature. And okay. So we'll do this problem together. I'm gonna make some space on the board. Again, if you're watching the recording, you can find the worked out problem on our annotated note. Okay. So, what are the first several steps? First thing first, we're solving for the total number of mole, right? So my N total at equilibrium, that equals to my PV equals to over RT. And this part is just plugging numbers. Right? My pressure is 2.175 atm. My volume is 32.80 liter. And my R, since I have atm and liter, I want to use something of the same unit. 0.0821 atm per liter per mole per Kelvin times the temperature of equilibrium, which is 4,000 Kelvin. That gives me 0.2172 mole. Right. Just plugging numbers, nothing fancy. That's our first step. We're done. Second step. Solve for the extent of reactions. How much reaction is taking place? What's the extent of reaction? What's C? Now, typically, we set up our initial state, our change, our final state. Right, so what do we know? We only have two species here. So we have O2 and elemental oxygen. So initial state, my O2 is 0.1500. So all in mole. My oxygen initial state is 0. Right, the change is the stoichiometric coefficient. In front of my O2, that's only 1, so negative C. In front of my elemental oxygen, that's 2C. Right, so in the final state, what are we looking at is 0.1500 minus C, and my final state is 2C. What else do we know? We know N total, right? So my final state is my equilibrium state. So we know that this sum gives me N total, which is 0.2172 mole. All right, so we can solve for the extent of reaction to get our C equals to 0.0672 mole. Right, so that's our second goal. Nothing fancy, just like initial state, final state, change stoichiometric coefficient, and use what we solved in the first step to get the extent of reaction. Okay, third goal, calculating our partial pressure. Right, so our partial pressure, which is, well, defined as the mole fraction times the total pressure. So what is our partial pressure for, like, say, oxygen at equilibrium? Right, so this one, I want my total pressure, so 2.175 atm times the mole fraction. Right, so mole fraction is the number of mole of O2 divided by the total number of mole. That's mole fraction. The same applies to our partial pressure of oxygen, elemental oxygen, that's total pressure, times the change here, which is 2 times 0.0672 over 0.2172. And this is something we know. Right. And since eventually I want to divide my partial pressure over like P naught, which is 1 bar, I'm just going to translate it into 1 bar. You can do that whenever you like. So this partial pressure comes to be 0.8402 bar, and this goes to 1.364 bar. Okay, That's our goal 3. Now we have the partial pressure of my species. The next one is, well, plugging into my definition for equilibrium constant. So the equilibrium constant is the, well, partial pressure of O2 at equilibrium divided by P naught to the stoichiometric coefficient of O2, which is -1, times the partial pressure of oxygen elements at equilibrium over P naught to the stoichiometric coefficient of oxygen, which is 2 here. Right. And these are just numbers we already solved. The stoichiometric coefficient we already solved. So my Kp naught, I'll give you the number, but you can do it later on, equals to 2.214. So note that my equilibrium constant does not have any unit, right? All my unit will cancel out. And at last, we're ready to calculate my delta G of the reaction at 4,000 K equals to negative RT ln Kp naught. And that gives me negative 26.4 kilojoule per mole. It tells me that's a spontaneous forward reaction to reach equilibrium there. All right. So if you like all of a sudden just look at the answer key, you'll be like, hey, this is too complicated. How can I know how to set it up? The nature behind it is like reading the question and do these steps in your mind and say like, what do I need to do to get my final answer? Do I have enough information if I do it this way? Right, so don't jump too fast and say, let me just start doing calculation. And after like 10 minutes, you figure out you're on the wrong path. That's 10 minutes is wasted. All right. Okay, so that's one example question together. One more thing. Now, for equilibrium constant, we already defined it. There are different versions of equilibrium constant. Now, for example, we defined it using partial pressure, right? So partial pressure Pi equals to our mole fraction times the total pressure. Or if you write it out, you can have the number of mole of your species Ni times RT over P. Or if we want to define, let's say, a equilibrium constant based on its molar concentration, where molar concentration Ci is defined to be number of mole Ni over V, right? So originally, what do we have? So in here, what are we saying is my Pi just equals to Ci RT, right? So it's my Ci equals to Ni over V. Right, so starting from my original definition of Kp naught equals to the product of my partial pressure over P naught to the stoichiometric coefficient. And in here, we know that Pi equals to Ci times RT. Right? It's the same to say like we can replace it to say Kc naught. So that C means that's equilibrium constant for molar concentration. That's the product of my Ci equilibrium divided by my standard molar concentration to a power of stoichiometric coefficient, where my C naught is 1 mole per liter. Nothing fancy, just to show you like there's like different versions of equilibrium constant. All right, and then we have 10 more minutes. I want to go one step further, right? What we did is we defined equilibrium constant. We demonstrate in how to use equilibrium constant. But so far, we're only talking about one single temperature. But even if, in reality, you can run a reaction, you can have equilibrium constant at different temperature, and your equilibrium constant will change with respect to temperature, like your delta G will change with respect to temperature. So in this part, we'll spend the 10 minutes to derive the Van Hoff equation, which tells me what is the temperature dependence of equilibrium constant. In the next lecture, we'll go over examples to see how do we use the Van Hoff equation. Now again, for these kind of derivation question, right? So what are we asking for? So translating what the question is asking for into mathematical expression, this is an important ability. So in here, we're looking for temperature dependence of equilibrium constant, or we're talking about how does my equilibrium constant change with respect to temperature. Or the expression we're trying to solve here is the differential of my K log P over dt. Right, so the Van Hoff equation is trying to solve this differential of your log Kp over dt. This is where we're going to start from, which is my log Kp equals to negative delta G over RT, which is the same as this equation here. Right, so using this equation and also thermodynamics relations and also our basic calculus, we'll derive the Van Hoff equation together. And likewise, if you're watching the recording, even if I'm doing the derivation on the board, you can see the derivation on our annotated note. All right. So in this case, what are we looking for? So first thing first, right, we want to start from where we know and construct what we're looking for. So what's the best way to do it? Take the differential over t on both sides of that equation. So we end up getting d log Kp naught over dt equals to d over dt. On the right-hand side, we have negative delta G naught over RT. All right. And then what do we have here? So in there, we have a little bit more complicated relations. Now you have temperature in there. You have like 1 over RT over there. You have delta G naught, which also might be a function of temperature, right? So we want to focus on the right-hand side and see how can we further simplify that expression here. So first thing we do, let's separate this negative RT term with my delta G, right? So obviously we can use our dxy equals to x dy plus y dx. Right? We use calculus, but just a very simple calculus. And using these relations, we can rewrite that into, well, negative, or delta G naught. So let's say this is my x, and the negative 1 over RT equals to my y. So writing it out, we have delta G naught times d over dt of negative 1 over RT plus, well, negative 1 over RT d delta G naught over dt. All right. And the left one we can solve. This one is very straightforward to solve. That means R is a constant. We're just taking the differential of 1 over t. So solving the left one, we get delta G naught times RT squared over 1. Right, so left one is done. What we're looking for in this term, right? This one is like negative 1 over RT. This one is fine. We want to think about what is my d delta G naught over dt. All right. So for here, we have several things we want to use. First thing, what is my delta G naught? Again, whenever we're stuck in this class, thinking about what exactly am I writing down. So the delta G naught here is the sum, well, it's my Gibbs free energy of the reaction. Or the other way to put it, the Gibbs free energy of the reaction equals to the sum of my stoichiometric coefficient times the molar Gibbs free energy of each species inside the reaction. All right. So this term here, the stoichiometric coefficient term, this one is not dependent on temperature. We don't care about its dependence on temperature. So this thing thus becomes the sum of my stoichiometric coefficient times d Gmi over dt. That's our molar Gibbs free energy. All right, so what is this term? This one is the change of molar Gibbs free energy with respect to temperature at constant pressure. Right? It's at constant pressure because of that little nod tells me that standard state. What do we know about a temperature or pressure or volume dependence of a state function? Right? So that reminds us, go back to the thermodynamic relations. Now, what do we know about dg over dt at constant p? So my dg over dt at constant p is negative s. All right, so if this derivation ever happening in the exam, I might hint you might want to think about the Maxwell relations. Right, but the actual logic is looking at it. We're looking at the physical term of this one. It's the change of my molar Gibbs free energy with respect to temperature. So this entire term thus becomes negative molar entropy or standard molar entropy. And taking that into consideration, what do we have here? We have a sum of stoichiometric coefficients and my molar entropy of different species. And this sum gives me the negative delta S of the reaction, or the standard entropy change of the reaction. All right. And then taking this back here, what do we have? We have my negative, and this term becomes negative delta S naught of the reaction. All right. And we can further simplify this to be delta G naught over RT squared plus, because my minus and minus cancel out, RT delta S naught. So if I take my RT squared out to be 1 over RT squared, delta G naught plus T delta S naught. All right, and what is my delta G naught plus T delta S naught? That's my delta H naught. So the take-home message here is we find out an expression for the change of the equilibrium constant with respect to temperature. That equals to delta H naught over RT squared. And that's our Van 't Hoff's equation. Right, and then what's the power? Like, why do we care about it? That tells us if we run the reaction at different temperatures several times, we will be able to establish a relationship, again, between something we can measure. Right? So equilibrium constant is something we can calculate as long as we know the composition of my material at a certain temperature. Right? So we can calculate delta H naught of the reaction. Or vice versa, right? Once I establish that relationship, and now at a new temperature, I have my equilibrium constant, I have my delta H, and at the new temperature, I have my delta H. I can use that delta H to go back and estimate what the equilibrium constant is at a different temperature. In reality, typically, because this one is not giving you a linear relationship, so it's a little bit hard to read. So in reality, normally people use calculus again. So we know that differential of 1 over t over dt equals to negative t squared dt. Right, so using this term here, people typically plot d ln kp naught over d 1 over t. And that gives us negative delta H naught over R, which is a linear plot. All right. So in our next lecture, we'll see what is the power of the Van 't Hoff equation and how do we actually use the Van 't Hoff equation to solve chemical problems. I know I'm behind, so I don't want to rush. So we will spend more time talking about chapter 6. I might cut short on how much we want to discuss on like phase rule and so on. But whatever we finish discussing on next Wednesday, that's going to be everything I want to cover for this lecture. So next Monday, I'll also give you more information regarding the final exam. And as a final reminder, your survey for midterm 2 and the regrade requests are due tonight. So if you haven't done that, please do that within our due date. Okay, I'll see you next Monday.